All right, we are at time. So, hello all. Thank you for joining me. This is the continuation of Flojo University webinar series. This is our advanced webinar. Today, we're doing one of our high dimensional workflows. Let me share my screen and bring up some slides that I'm going to use to start the webinar. All right. And that'll make for a better introduction too. So there we go. Hi, John Quinn. Today's high dimensional workflow is one of a series of just workflows that we're going to illustrate a series of our tools put together in sequence to show how one might analyze high dimensional data from start to finish. Each of the application scientists at Flojo is going to pick out their favorite set of tools to walk you through. And so my particular favorite set of tools are, well, I'll talk just a smidge about Peacock in that there are fewer QC tools than we're going to do high dimensional webinars, but I'm going to use it. I'm going to use it in the webinar. So I'll mention there, I'll gray it out. I won't talk extensively about it, but primarily this webinar is going to be about T-Rex, MEM, and Embed. And we're going to walk through 31 parameter data off of an A5SC spectral, spectrally enhanced cytometer using Flojo version 10.10. So with that, hi, I'm John Quinn. I'm the Director of Science and Product Development at Flojo, aka BD Biosciences, the infamous. Hello again. Can you hear me now? All right. Thank you, Zoom, for kicking me out and then muting me. Good way to start a webinar. So nowhere to go but up. All right. Manual analysis. Back to the top of the slide. I'm starting a high D talk with some manual analysis just for a little compare and contrast, and largely because I want to point out that there are a few advantages to manual analysis. Specifically, some of the pros of manual analysis so that you'll be able to name your population something sensible as you step through analysis. You can draw a gate, for example, type in a name of, Apologies. Zoom appears to want to kick me out every couple of minutes. Fun. Let's hope that stops. Okay. All right. And actually, I don't know if I finished the bottom. The cons of this of doing manual analysis. I think probably if you hear at a high D analysis talk, you've probably run into a few of these things. When you're making your gates, you're only considering the two parameters that are on screen at a time, perhaps the ones upstream in pairwise consideration. You're not making the gates thinking of all the parameters all at once. Your population names are maybe only reflecting what you've looked at thus far in an analysis. Identifying a difference in some condition might require looking at all of the plots, for example, that I have on the screen that I pulled out of a recent paper. Visualizing a data set can be difficult. It may take all of these plots to see it. And so if we go to high dimensional analysis, then that's going to help with a lot of the negatives. It'll be less heuristic. You'll be considering all dimensions all the time, or at least all the ones that you care to consider by feeding them into the specific algorithm of choice. It'll provide holistic visualization. A plot like this on the right, where I'm showing like a UMAP plot of some large data set, allows you to see every single phenotype all at once, all on one plot. And identifying differences can be much easier. So, for example, the plots on the bottom of the screen there are showing comparison between 3 different donors. And all you have to do to compare those plots is to look for populations that are over or underexpressed in one or more of the donors, and it should stand out right away, no matter which parameters you're looking at, because you can pick the dimensionality reduced parameters, such as UMAP 1 and 2 here, and just see all of the phenotypes all at once. However, the cons that UMAP or tSNE or most of the clustering algorithms, they'll produce a slightly different result each time that you use them. Hence, we're going to talk about this workflow today, where I'll mention, again, just briefly, Peacock was used for quality control, but then T-Rex is a tool that can handle nearly the rest of the analysis, that can do dimensionality reduction, it can do clustering, and it can do identifying of interesting populations, things that vary from perturbation to perturbation between 2 different, say, I don't know, treatments or 2 different demographics, something of that kind. MEM is going to be the tool, Marker Enrichment Modeling, that will step in for that population naming step to make that significantly easier. And then we're going to use the tool Embed to forward propagate results from this experiment to any subsequent experiment that we might do, allowing for direct comparison between these experiments and populations, even in a high dimensional realm. And I think that's the tool in the end that really makes a high dimensional analysis perhaps an actionable step or a set of steps that you can take to look at anything downstream and in the future. That if you come up with some kind of conclusion, you can test it moving forward, you can apply it moving forward. All right, and so what we'll do here is I've got 14 or 15 slides, Zoom willing, that will allow me to tell you a little bit about the theory behind those algorithms, how to use it, and then I'll open up that 31 color workspace and step through this analysis using T-Rex, MEM, and Embed. Okay, Peacock used to do some data cleanup. Only thing I'm going to say about this slide is that I think that data cleanup is even more important, and it's super important on manual data analysis, but it's even more important on high dimensional data analysis, and that you're less likely to look at every single pair of parameters with many parameters, many combinations. And so having some kind of algorithmic approach to cleaning up technical variance in the data as a first step populations it finds by whatever distance metrics it looks at. But it's going to require you to input some kind of condition that you'd like to compare, two things that you'd like to compare against. So the workflow here is, and the example picture being shown here, by the way, is just 2 time points, day 0 and the follow-up experiment, day 28. What it's going to do is do some kind of dimensionality reduction on the data that you feed it. And you'll have to concatenate all the data together into one big file and say, here's the half that's one condition, here's the half that's the other to run this algorithm. And it will do either then tSNE or UMAP. It is your choice within the algorithm, which you prefer to do. It will then use k nearest neighbors clustering to identify regions within the tSNE or UMAP plot. It will essentially say, who are all my neighbors? Who are the nearest neighbors? And there's a few tunables to say how many neighbors to find, etc. And then it's going to look between those regions to see, are there any regions that have a significant increase or overrepresentation of one of your 2 conditions? So in this example on the screen here, it's looking to see if there are significantly more cells from either day 0 or day 28 in either one of these, in any of the regions that it finds. If it finds regions where this is true, then it's going to use a more refined clustering algorithm called dbScan to go through and create clusters centered on the regions where there is a difference. And so what I think makes this algorithm particularly powerful is that we're going to talk about a variety of high-D workflows in this series of talks. And the general gist is going to be that you're going to use these tools to visualize the data. You're going to cluster them. You're going to try to figure out which clusters are different, which ones have some kind of effect. And this particular tool gets directly to the point where you want to end up. Where's there a difference? Why do I care what the clusters are? Because I want to see what the difference is between these 2 conditions. As this little graphic is illustrating, you can set what your thresholds are, how big a difference has to be for it to highlight it, for it to count it, for it to use the dbScan. You can set 2 levels thresholds, so here's 85% and 95% enrichment compared to the other time point. Again, it could be any perturbation that you'd like to feed into the data. So you can, again, just imagine that it finds some kind of locus point and then uses that to figure out where the cluster should be formed. And then to access this tool, you're going to go to, in version 10.10, you're going to go to the algorithms band within the workspace ribbon. You'll pick your plugins dropdown. However many plugins you have, you'll find T-Rex in the list. You'll start it up. We'll talk super duper briefly about how to get a plugin. The rest of the tools we're going to use in this workflow are actually built in. So we don't have to talk about getting plugins other than T-Rex for this workflow. And then, as almost all algorithmic approaches begin with, you'll have to specify which parameters you'd like to allow the algorithm to consider. It'll generally be most of the compensated. I say most in that as when you're using any other dimensionality reduction or clustering, you're probably going to leave out anything that you pre-gate during the cleanup phase. So if you've, I don't know, used a live dead die, please, you've used the live dead die to discriminate dead cells. There's no reason to use the live dead die in your tSNE or your clustering, etc., in that all of the cells have roughly the same intensity of that die. And so what you'd be telling the algorithm is that all the cells are the same. And if the primary job of these kind of algorithms to separate things that are different and put together things that are the same, some piece of information that says they're all the same, put them all in one cluster, in one island on a tSNE or a UMAP map, then that's not particularly helpful information. So we would leave those parameters out. You'll specify for T-Rex purposes, what are your 2 perturbations? Here, I've made most of the slides from the data set that I'll show you. So it's going to be the perturbations that we'll look at too within the data. We have a keyword where we put in some demographic information where we divided the subjects into old or young. I will not tell you what the threshold I used to separate old and young. It's probably better for all of us. But we had data that fell into 2 distinct groups. We went to see if there were different populations that appeared for those 2 groups in 31 dimensions. You've got a couple of tunables, k, the number of nearest neighbors that you'll look for, and an epsilon number that sets the threshold for what is a region for DB scan. I will say in general, the defaults are going to be just fine. You can tune them if you'd like. The paper, which is right here, Barone, Paul, Muehling, etc., eLife 2021, went through and did just some testing, and they came up empirically with a good set of defaults that seem to work pretty well. So you can start at least with those values, I believe. The next section here is just the bins, where you'll put in brackets the different regions of overexpression and underexpression you'd be looking at. So the middle one will just be essentially all the both, or you have representation from both of the categories in it. So here, for example, I'm looking at 0 to 5%, 5 to 15% on one end, so the lower end for the old folks, and then 85 to 95 and 95 to 100 on the high end for the young folks. And then there's the middle bin. You can pick between tSNE and UMAP, and then you'll have a few tuning parameters here for either, well, if you use tSNE, then you'll be able to set the perplexity and the iterations. If it's UMAP, then you won't set those. And then there's the minimum clustering size. So as I described, that algorithm is looking for, a small locus where there's a difference between two conditions, and then you'll cluster around that locus. You can imagine that without a threshold, T-Rex will find some very small populations. If you were uninterested in finding a cluster of 3 cells, set the minimum cluster number up a little bit. Up to you, and it'll be based on your biological question and the particular population you're looking for, what size of appropriate minimum is. I think I typically go for, if I've got a decent amount of data, like 25 cells or something like that. Okay, the outputs. So T-Rex is then going to produce a handful of derived parameters. There'll be a clustering parameter that will auto-gate on, so you'll have a series of clusters. You'll have a T-Rex % change. So that's that fold increase, decrease, and you can plot on that. You can use it as a heat map parameter, which is kind of nice. And then you'll get whichever two, whatever dimension reduction tool you picked, you'll get the X and the Y dimension of that tool. And then this is a tool that was written by the group at Vanderbilt and exists in R. And so you will also get a series of outputs in wherever you've saved the workspace. You'll get a folder with the same name, and you'll just get all these extra graphics that R kicks out and gives you visualizations, such as that, like a gray, tan, blue plot that I've used on these past couple of screens, so you can help visualize if you'd like. One of the benefits of using somebody's tool where they put some thought into it and come up with a series of standard outputs. So fun. All right, next, MEM. I am looking at the chat box too, by the way. Probably more questions will come up, I assume. Oh, and thank you as I speak to that. Yeah, appreciate it. I like the Grogu myself. Okay, so moving on to MEM, and I'm looking for questions if they pop up in the chat. Marker enrichment modeling. All right, so the output of T-Rex is going to leave us with cluster 1, cluster 2, cluster 3, etc., which is not particularly informative. And this is the point where you could go into that cluster. You could use a variety of tools, the cluster explorer perhaps, to try to figure out whether a particular cluster is up or down, expressing any particular marker. So expressing higher or lower, greater intensity, lower intensity, up or down expressing wasn't particularly good English. Okay. Or we break out MEM, which is paper-peer, a brief communication from nature methods, a way to name or characterize a population based on what it's expressing in comparison to some reference. All right, MEM is always in comparison to some reference, and you can pick what that reference is. And so what the MEM is, it's basically an equation, which is listed right here. It's the magnitude of expression for each one of the parameters in your data set for your test population compared to that reference, plus some just correction factor for if a population is really spread out or very, very diverse or distributed compared to another. So we look at the interquartile range. You can see from the equation that if they are essentially the same, this correction factor just goes away. But if your reference is, say, much different from your test, then it'll have an effect. You have to correct for, again, a nice, tight, concise population versus a spread one. Okay. MEM can be either positive or negative, in that if the reference is brighter than your test, you would get a negative number here. So we'll just add on a plus or minus based on that measurement. I see the brackets there. And then we'll do a linear transform to normalize it to a scale, a magnitude of 10, so negative 10 to positive 10. And so the end result, if you take each one of the markers in your experiment and name a population based on whether it's 0 to 10 expression plus minus for every particular marker, you'll get something like this as a MEM name. I really like this approach for a couple of reasons. One, it is not dependent on you and I agreeing what some combination of parameter expression means. We don't have to agree that those are CD19 cells or B cells or some specific kind of B cell. The name is the name. You can additionally add some text later afterwards and say, this is a take your pick, and use that for discussion and for making ease of discussion easier. But you'll just have essentially a vector that describes what this population is without a lot of heuristics needed to agree on. So that's a real positive thing. Also, the 0 to 10 scale allows for some nuance. Things can be not just positive or negative, or not even just bright, dim, or negative. 1 to 10. You've got a range of expressions here to give you the language and nuance to really describe fine differences in a high dimensional population. And 3, I think I said maybe I like 2 things, but maybe it's 3. I do like having the ability to have the name in respect to a reference that makes sense for the biological question I'm asking. So 2 examples of what you might pick as a reference are shown on the screen. So one that I think is particularly useful for clustering is to pick all of the other clusters as the reference. So you've got some sample, you use clustering to divide it up into multiple populations. If a group of cells stand out as a cluster, an algorithm has gone through and said, based on the sum of the measures, these cells are different from the rest. And so that would jive completely with this approach from MEM of saying, well, why are they different? What made these cells different from all of the rest? So for every single cluster, all of the other clusters, it's like almost like an FMO. All of the other clusters are your reference. Why does this one stand out? The other option would be to pick a particular control population, maybe something negative, unstained, something to that effect, and say, okay, this is background. Tell me how everything compares to background. So if you really want more of a standard, this is relatively high expressing, low expressing compared to all one single reference population, that might be the way to go. There's also an auto reference tool that will just use the range of the scales as an option. That was actually a follow-up paper to the original MEM. Okay, and to use MEM, you'll just go again to the workspace band and algorithms band and the workspace ribbon. Right next to plugins, actually just 2 down is MEM, where the drop-down menu includes 4 different options for MEM. You will always have to start with creating scores. The first thing to do is create scores before you do anything else. It will put a name, append it next to the name of your cluster. So we'll say cluster 1, but then have your MEM score next to it, that CD19 plus 10, etc. There are options to change the MEM threshold. So we will allow you to pick how large a MEM number has to be. So plus 10, plus 9, plus 8, etc. for it to show up in the name. You could simplify your MEM name by saying, filter out anything that doesn't at least get to plus 2 or plus 3. I don't care about the minimal difference in expression, perhaps. And I'll accept that loss of resolution essentially for simplification of names. You can also use MEM to merge nodes based on MEM scores. So if you end up with 2 clusters, you've overclustered perhaps, and they have the same MEM score as a name, merge them together. You can also export the MEM scores. This is a recent addition to 10.10 and shown just right here. You pick that and you can produce a CSV file that just gives you a chart of your population, its MEM name, and then the MEM score on a per parameter basis. So built in. Okay, so once you pick MEM, this window pops up. Like almost everything else that we're going to talk through, you'll pick which parameters you're interested in. same thing. I would assume if you've already gated on some population, perhaps you're uninterested in showing it in the MEM score name. In that, especially if you pick the auto reference, you'd be very dull to have a bunch of T cells and to tell me that they're CD3. But you may want that to pop in, especially if you're using some kind of specific reference population. It's up to you. But pick some parameters that you want to use for your naming. Here is your what kind of reference shall I use. There's auto reference, which is use all of the other clusters. There's user defined reference, pick a specific population out of your gating tree. And there's reference, let's just use the range of the data. So things towards the left of the screen tend toward MEM 0, things towards the right tend toward MEM 10. Everything in between is fair game. I have to pick which population if you're using user defined. You've got an IQR threshold. So that term where we're dividing something, the test versus the reference IQR, if the bottom term would go to nearly 0, that could blow that term up. So we set a threshold that it can't be worse than 0.5, just to keep it from getting crazy. If you've got very, very small numbers in a fraction. And then you've got the marker inclusion threshold. So that's how big does a MEM score have to be for me to show it in the name? At least a 1, right? You don't want a 0. Wouldn't be very interesting at all. Okay, and then when you hit OK, here's how it looks in FlowJo, where you have your cluster names, and then in parentheses next to it, you'll get a MEM score for each of those. And I'd probably set this MEM score to be at least a +2, so we don't see any +1s in there. Okay. Last tool we're going to talk about here is Embed. So this is the tool that addresses, fantastic, I have found that there is a particular population in my tSNE plot or my UMAP plot, and it corresponds to a cluster, and it's the really meaningful one in this experience. I want to go look in the next experiment, and see if I see that same cluster, and how is it over, is it underrepresented, etc. How do I do that? How do I forward propagate the learnings from this experiment to the next experiment? Why, I could use Embed for that. So it is a method of calculating our dimension-I reduction or cluster values and pushing them forward, and it uses near neighbors as a basis. This one I don't have a paper for. It is patent pending. We will hope to publish it at some point in the not too distant future, but I've been saying that for like a year now. It is on me to do it, and it's a busy life. Anyway, the way that this thing works is that the input space to the data, these are the parameters that you've measured. So in both the experiment that you've already analyzed and the one that you have just collected and have not yet analyzed, you've measured a set of parameters. And if there are some common parameters, so you've measured CD3, CD20, CD56 in both experiments, that's your input parameters. And we can look for every single cell in the new experiment at the previous experiment and say, which were my nearest neighbors? And so you can use some kind of metric, Euclidean, Manhattan, whatever you'd like to do. You've got a few choices built in to say which cells are most similar to this one based on the input parameters. And you'll find them. So, okay, it's this N1, 2, 3. Terrific. We can then interpolate in the dimension-I reduced space the tSNE or UMAP XY coordinate for those nearest neighbor cells and apply them to the new cell. And so the most similar cell has the most weight, and the second most weight, and so forth. And then we would be able to plot that new cell onto the same tSNE or UMAP plot. We could also do that with cluster results, and we'll just handle that slightly differently. I'll point out that there is a spot where you can deem whether a parameter is a clustering number or a dimension-I reduction number, in that when you cluster the data, if you look at the nearest neighbors and they're from cluster 1, cluster 1, cluster 1, and cluster 2, you don't want to interpolate at that point. You don't want to end up with the new cell in cluster 1.2 or something like that. You want it to be in cluster 1. And so we use a voting procedure if you deem a parameter a clustering parameter. All right. And so just give you the gist of how it works. Off some public flow repository data set, the first row is showing one sample. The second is showing a second sample. So we've run tSNE and UMAP on the full data, just showing a lymphocyte gate on each one of these. and showing where the lymphocytes appear in the tSNE and UMAP plots. We then use Embed on the second sample without having shown it at all. Sample one, just using Embed off the first to generate tSNE and UMAP parameters. The same general populations pick up. If we make that same lymphocyte gate, we see that the cells appear in the same positions. So that's just forward propagating based on the parameters that are in common, and doesn't have to be all of them. It has to be enough. More is more. And putting it on the same scale, the same axis, the same dimensions of like tSNE and UMAP and so forth. Okay. The question, all parameters not appearing in the assigned MEM population name do not show a different expression compared to the reference, right? Correct. Yeah, that's exactly it. MEM is ordering the parameters actually in the order of importance. So the +10s, if you have any, all the way at the beginning, and then we cut it off at whatever threshold you say is not interesting. And usually we stop somewhere above 0 because it's just not interesting to try to identify what the population is. Good question. Okay, so your inputs to Embed. We've got a full set of instructions right in the menu screen that pops up when you start Embed. It's much more simple than that much instruction leads itself towards. Basically, you select the parameters up here that you want to forward propagate, and the parameters down here that you will allow the algorithm to use to figure out if these are nearest neighbors. And that's pretty much it. So you can see here that I've selected some UMAP parameters, and I've selected one clustering parameter, and then I right-click in this box here to say it is a clustering parameter if it is, as opposed to dimensionality reduction. So this says don't interpolate. Picked essentially, again, everything here that is beyond the pre-gating cleanup stage, anything that I wanted to use to learn on. But even at this point, you know, if you've already identified T cells to do most of your work, you might want to put CD3 in there. I've unselected it there, but just making sure that you've got T cells compared to all the rest of the data would be a useful thing to do. Okay. You've got an input and an output quality score. So just down here, I called it small adjustments, in that the defaults are pretty good. I don't think you have to adjust them unless you want to tune a little bit. The input and output quality score are interesting. I will, when we actually go through the experiment, I've picked an example file to forward propagate it to that has a lot of cells that are novel to that file that aren't visible in the previous file. And so I'll show you the impact of that. But the gist is that we will always find a set of nearest neighbors. But how far away were those nearest neighbors? We'll tell you that through an input quality score. And then once we interpolate it, how far is that cell from the nearest neighbors? And so those will probably walk together, but not always. So we'll give you a separate output quality score so that if you want, you can graph the quality score, both quality scores of every given cell, and gate on the ones you want to look at. And so I'll show you that slide in a little bit, make that more tangible. So you can train on a certain number of events. You can set the number of nearest neighbors. We have the default set at 7 now. I think somewhere between 3 and 7 is going to be optimal. And I think if you use a smaller number, that puts more emphasis on the most likely nearest neighbors. A slightly larger number like 7, you know, allows you to avoid outliers. So I don't know that there's an absolute right number there. I guess we'll keep testing empirically, but it seems you get pretty similar results between like 5, 6, 7. So we've made 7 the default for now. You can add a random suffix to identify any populations on if you want to run a second time or a third time, etc. We've put in a variety of distance functions. Some are recommended. I suggest just using the recommended ones. There's also an option to force cells to be placed in a cluster. And so what that gets to is if you pick 7 nearest neighbors, and the nearest neighbors are in cluster 1, 1, 2, 2, 3, 4, 5, 6. None of those clusters really dominated that. It's pretty spread. We'll just assign that cell to cluster -1 so that it actually just gets pushed out of your standard cluster analysis and set aside as didn't really fit into any cluster, and an outlier group essentially. Unless you check the force all cells to be placed into a cluster. At that point, whatever cluster has the most votes amongst the nearest neighbor wins. Even if there's a tie, we just pick whichever one comes first. Better than nothing if you're forcing it. So that's that. So you can force every cell to end up with a clustering result. Okay, here's the outputs from Embed. You'll get those two quality score parameters. You'll get, if you've done the steps exactly in the previous one where I did one T-Rex clustering and then a T-Rex UMAP 1 and 2, you'll get each of those as parameters that get forward propagated. Okay, and then if you plot the quality scores, you'll get something like this. You'll get some kind of picture of, OQ for output quality, IQ for input quality, just some random numbers that if you run Embed more than once, you can tell which parameters go with which run. And then a scores that'll generally go with, like 0 to 1 or so. For input quality, output quality could be a little more. And, the things down here in the bottom left are the ones that are best. So here's the picture of the one that has a pretty wide range of quality scores. As you get farther away here, that implies that there wasn't a good nearest neighbor, and the output means the cells are fairly distant from any of the islands in the tSNE plot, etc. So if you want the cells that modeled absolutely perfectly, you would pick something towards the lower left. If you're interested in seeing what cells are novel for the follow-up experiment, that's the ones up here, the ones that did not have equivalent cells in the initial experiment. So those actually could be the more interesting ones. You may want to gate on the upper portion or not gate at all and just see how everything fits in. It's up to you. Giving you a tool, use it as makes the most sense for your particular experiment. Okay, so that's it for slides. I'm going to step out of that. I don't want to even say anything about Zoom at the moment. Seems okay. And let's open up a workspace, and which to start. That was 1, and that other one is 2. Okay. So I have pre-calculated much of this. It's a webinar. We can do this cooking show style where I say, and then you would click the button and wait a little bit, and we don't have to wait then because no one wants to have to wait while we watch things calculate. But the gist, I've got a series of donors here that are full stained with my full panel. And I've set one aside up in a group I called follow-up study. So for these donors, I went through, I ran Peacock, I got some good events, some bad events. I'm moving forward with the good events, a few standard cleanup gates, live, single cells, there's a dump gate in there, so some negative, just a big, large scatter gate to take a few things that are towards the edges off. Looking at CD3 T cells, the rest of this panel is aimed specifically at flavors of T cells. Made one gate here just to pick out the CD8s. Let's go CD8 positive, CD4 negative, and use, so if we've used live dead 3 and 4 versus 8, that leaves us something like 27 other parameters to deep dive on what are all the subsets we might find. At that point, I clicked this population. I said select equivalent nodes so that we highlighted the CD8s on all of my donors. I have annotated the age here as a number, 1 or 2, indicating old or young. No more comments on that. Right-clicked again, said export/concatenate, chose the concatenate option. Under the advanced options, I chose to add my keyword. So I've got those old young keywords in here, called it age. So I just picked out age, said okay. I might as well just say okay. I've already done this, so we don't have to concatenate again, but we can, said okay. Kept all the events. There were relatively similar numbers of events from every one of the populations. So every one of the files. If we don't have exact numbers, I think that's okay. We've got tens of thousands of events for each one of these samples. So if one is 35,000, the other is 37,000, I don't think that's going to overweigh one particular sample versus the other. All right, and then hit go. So the file appears. There it is now I brought it back into FlowJo as my CD8 positives concatenated. Okay, hiding the results. All right. To then run, I guess, stepping back one second, I should say, scaling is super important. When you run any of these clustering or dimensionality reduction tools, I think it's any of them, I think it's every single one, FlowJo uses the bin space, the visual space, just like you see it, as the inputs. And so if you have a bunch of white space on either end and all your data is compressed into the middle of the plot, just like it looks like it's all compressed in the middle of the plot to you, it does to the algorithm as well. It's more likely to say these things are all similar and less different. If you trim out the white spaces at the edges, maybe even put a good width basis on your negative population to minimize the variance across the negative. So you say that differences in negative are less interesting than differences in actual antibody binding in the positives. That'll give you a nicer result. So just a moment to say it's probably worth taking a look at your transforms, making sure everything looks good, is on scale, and you've trimmed out any excess white space. And then we will start the algorithm. Okay, so I click on the population that I'm interested in. One more step for T-Rex. You have to feed it two conditions. So for T-Rex, I'm giving away what it's going to look like in the end. I think that's okay. It doesn't have to be a surprise. I have that age parameter as that age keyword added as a parameter now. I'll show it as a histogram. Looks like I've got a few more cells that came from from young people compared to old. Just makes sense. Young people are just, more, they're go-getters. Anyway, if I right click on that, I could say create gates on peaks. We auto create some peaks. We can name them old and young. My zoom controls are in front of my graph, so I have to stretch it out to close it. So that's this old and young population there that you see in my workspace. Okay, so now when I say workspace, algorithms, plugins, and T-Rex, I can pick old and young as my two conditions for pre-treatment and post-treatment. The T-Rex algorithm, I think, just uses language that maybe implies that there is a treatment that is the difference between your two things. In this case, the treatment here is time passing. So fair enough, whatever it might be that you're looking to study. At the top is a list of all the parameters. Be sure, let me unhighlight that. Be sure that you pick the compensated ones. They are actually sorted at the bottom in this algorithm. Sorry. And as I mentioned, we may leave out things that we gated on. And so we have gated on CD3 for the dump channel. Don't need autofluorescence, 8, and live dead. And then we'll feed it the rest of it. Okay. Leaving K and epsilon, totally happy with bottom 5% and the next 10% above that being highlighted as my interesting amount of overrepresentation. Cool. We can do UMAP. That'll work. That means we don't have to worry about tSNE complexity or tSNE iterations. Minimum cluster size, set it to 25. Say OK. Let's see. I think this took maybe seven or 8 minutes to run. So that's if you can imagine, that's about what it would take for running 120,000 plus events over. I didn't use all 31 dimensions, but pretty close, 27 dimensions or so. So it's not too terrible for essentially the whole workflow. Okay, when it finishes, it pops out those derived parameters. And then we can double click on this and show what the data look like. Okay, so I have used the T-Rex UMAP parameters 1 and 2, and I've turned on the color axis here. So it's just a pseudo color. I've turned on the color axis and picked the T-Rex percent change. So at the low end, you've got overrepresentation of the first one, which was the old folks. And at the high end, the reds, we've got overrepresentation of the second one, which was the young folks. And so everywhere where it's, greenish and yellow, we have a mixture of both, and oranges too. And so it's really just like the reds and the blues that we're really interested in. So we would be interested in seeing clusters that formed around, the edges of this island in tSNE, the tip of this island down here, the edge of this island, maybe down here and right there, maybe right at the top there. So we expect that there's a few different spots where there might be some interest. And I've made a subfolder, a subpopulation called T-Rex clusters that I drop my T-Rex clusters on just so that I can minimize it if I care to. But there are our 18 clusters. And so if we go to the layout editor then, we could drag in just the total population, T-Rex clusters, make it gray, and then overlay all of our individual clusters in there. And we'll see where we've got the brighter colors. And, maybe I should change that light pink to something more dramatic so it starts out. I haven't used, let's go with like that color. There we go. Anyway, so wherever it's highlighted, we've got a cluster that's particularly different between older or younger. We could use that heat map as a Rosetta Stone if we'd like, to show the difference between whether is this more for the older people and more for the younger people. For the time being, it's just different. I think I'm interested in all the places where it's different. And so we could move forward with those clusters however we want. Could be time to break out the cluster explorer to see what they are. We could go to our high dimensional folder where we ran this algorithm, open up the T-Rex subfolder. We've got a bunch of outputs. So there's a bunch of plots in here that we could look at. Convenient to go right with some of these plots here. So you can see where we've got blue is the older folks, as we mentioned. Lighter red, darker red is the younger folks. We've got more representation. So, and there's our clusters that correspond to that. Some of these clusters will have been below my 25 cell threshold. So they didn't appear as actual clusters in FlowJo. They came out as clusters here to be shown in the R version of this. So that's okay. And there's other ones that tell you the numbers of the clusters and so forth. So some of those outputs can be pretty useful. Okay, so cool. Jumped right to where's the difference between our two perturbations. Awesome. So instead of doing any of those other steps I mentioned as a possibility, why don't we break out MEM? So to do MEM, I just highlight the clusters that I want to get a MEM name. I go up to MEM and say, give me a MEM score. All right. If there's any of these scores that I don't want, any of these parameters that I don't want used in the score, I could do that, like telling me it's got more or less autofluorescence. I mean, I guess if you want, you could do it, but I'm going to leave that out. They're all CD8 positive, so I'm going to leave that out. I don't care about the dump channel. They're all CD4 negative, and they're all CD3 positive. Although 3 does change expressions with stimulation, I could consider leaving it in. Yeah, whatever. Your call at that point. Here's your choices for which type of reference do you want. I'm going to go with the auto reference here because I do have a clustering result. And you could apply MEM to anything, but I feel like for a clustering result, it seems like a good thing. Leave the default for the IQR threshold. Let's see. Is there a way to describe the question? Is there a way to describe the detected difference between the old and young statistically? Sure. It is in terms of the language used in the paper is fold increase or decrease. And so what that just means, it considers the two things that you've put in that you're comparing, young and old in this case, to be two conditions that are separated by considerate time or whatever. And so it's saying in one spot on the plot, so one k nearest neighbors identified population, do we have a 95% fold increase of number of events from one condition to the other? And that 95% was because I typed in my upper range was 95 to 100. You could set it to be however large a fold increase you deem interesting to look at. Okay. So that is what the number represents. If your question is more like, oh, how do I turn that into a p-value or something like that? P-values are usually going to be used to talk about how repeatable that is. So if I had a plate full of data and 96 wells, half of them were old, half of them were young, whatever, and every single time a given population had more overexpression for young or old or something like that, you'd say with very high confidence this is repeatable because it happened 48 out of 48 times. So repeating and replicates are good for being able to turn something like a fold increase statistic into a confidence or a probability. All right. I'm going to say okay here. Oh, sorry. I was mentioning him. Marker inclusion threshold. Just left it at 1. That's the default. I'll say okay for now. You'll say okay down here. MEM thinks for a couple of seconds. and then it pops out some MEM names for the population long enough for me to get some more tea. But not more than that. All right. And this will be the one time I will actually run the algorithm live. We will use pre-baked high dimensionality workspace 2 to move on and talk about using Embed. But the MEM names pop out. Or we'll just pop open this web space. That's still thinking. Still thinking. There we go. Okay. All right. So relatively long in that, sorry, for this particular experiment, both the target and the sting are encoded in the name of every parameter. So you get like CD57, BB570. If you want shorter MEM names, you could not put the target in the stain name. But I do know that it's kind of nice for doing spectral compensation to have it there. So you win some, you lose some. Okay, so there's the names of all my populations that I have now got listed in order of most important thing first. So for cluster 1, the most important thing was that it is CD57 plus 4. It has moderate amount more of CD57 compared to all of the other clusters. So they won't all be the same thing, of course, or else any given one parameter wouldn't stand out. So there's looks like domination by 57, 45RA, Keller G1 as the markers that really were different between a variety of populations. We see we get down to MEM scores of +1s pretty quickly. If we're not interested in +1s and we decide that after the fact you can do MEM, change MEM threshold, maybe to 2. Okay, it shortens the name a little bit. We set up the threshold and there's a cluster or so that have no values greater than your threshold. It'll just say scores are less than marker inclusion threshold. Okay, also fair. We can, if we want, use this to merge any clusters perhaps that were over clustered. You can say merge nodes on MEM scores. This box pops up and it gives you the ability to enter a threshold from 0 to 5 for merging. What that means is that it'll look at each one of the parameters and say, what's the on a per parameter basis, how big a difference will I accept and say these are still the same thing. So we'll let you put in a number from 0 to 5 here, but I think realistically only 0 and 1 are good choices, or else you'll end up merging most of your clusters. And in fact, 0, I think, is a very legitimate choice. You can imagine that much of your flow data is binned on a 0 to 262,144 scale. So the fact that we've reduced already like 262,000 bins to 1 to 10, it means there is still some variability within each one of the 1 to 10 MEM scores. And so you're accepting a little bit of variability even if you put in a 0. And so I'll do that. I'll say, okay. All right. What happens is that any cluster that's unique just gets this not merged added next to it. And if you've got 2 clusters with the same MEM score, those end up, let's see if I can scroll down, getting merged and a Boolean gate is added. There it is. So 3 and 4 were merged, and there's just a Boolean gate that says, here they are. Here's the merger of those 2. So we keep the original. So you've lost nothing by trying it. But if you want to remake your overlay plot and show 3 and 4 as one population, you can do it. And then 5 and 8 were merged together. And then the rest were left not merged. All right. So one way to simplify an analysis, you can use MEM to do that. And then the last option for MEM is that you could export the MEM score as a spreadsheet. All right. So I will not do that. Okay. So next, I would like to now forward propagate these clusters to a new file that I haven't yet run tSNE on. I haven't done, sorry, I used UMAP for this. UMAP, out of T-Rex, haven't done the clustering, haven't done anything to it. I'm gonna bring up the other workspace in which I've already done this. This one takes a few minutes to run also, and we are heading towards time, so we don't want to wait for it to run. And let's show you how I did this. Okay, so I just put my concatenated file into the group with the follow-up study, and that you apply embed by dragging and dropping it. So I put them in the same group. And so what I've done here on the CD8 population is I'll pick my population that I was doing my work on down there in the land of 100%. I will say workspace algorithms embed. Same operation here, where we'll pick all the things that we want to forward propagate. So the UMAP parameters and the clustering parameter. And then for the clustering parameter, we want to say is a clustering parameter. Cool. And then go back in and say, what is fair game to use? And pretty much all of the fluorescent parameters here. And again, it doesn't have to be all of them. So if you've got a solid backbone panel, it is a way to forward propagate a tSNE result to something else, or UMAP or whatever. I'm going to leave the rest of this as the defaults, get an input quality, get an output quality, sure for training size, nearest neighbors, and distances, say accept. So it just takes a second for it to pop up. Oops. Where did I run it on? Oh, that's the other workspace. There it is. Okay. Two workspaces open. Mass confusion. Anyway, for this to pop up and say ready to drag, you will just then drag it and drop it to your target. So in this case, I would come up here and just drag this embed and drop it on the CD8 positives on this UGM donor 26 that has not yet been used. And this thinks this was another like 8 to 10 minutes or so. And then it pops out this new set of parameters. At that point, we can go onto this population. So here we've got those input and output quality scores. I'm going to double click on the input and output quality gate. So if I've just picked the really nice ones that have like exact matches, that very bottom spot, you get a distribution of populations that looks really, really similar to what we saw. If we pull back up the layout editor. So here's the T-Rex UMAP, old and young. Here's just this particular plot here of the new data file that I've added to it. And we would look and say, does it have a lot of cells on the left side of this? If I had to guess, it does not, it appears. It looks like a small population there, but we would test this. And so maybe this is more like the sample from an old person, perhaps. Old, relatively speaking. Older than young people, that's all. Okay, but anyway, it's like, you can see exactly where those cells fit in. If we then, and this is particularly an example where I picked something that had a bunch of different cells in it. You could include a higher percentage. Okay, so this population pops in here. This is probably some kind of cell that wasn't present in our example files that is in this new file. And so it's not really sure where to put it. And it ends up putting it sort of in between as a new population. So its output quality score is getting progressively worse. And it ends up there. As you go farther, you probably get more cells lumped into that. Like I'm not sure where to put a group and so forth. And then these populations thicken up as well. We went to all the way to like the lowest quality ones. Okay, well actually those are probably okay. They're probably just slightly distant from those two populations that were of interest. And then here's one that's maybe out in the middle of nowhere. Anyway, so that's how you could use the input quality score however you'd like to filter down embedding results, the ones that fit best or maybe are the most novel and perhaps the most interesting. Okay, and then so that's it. You just drag and drop embed to any other file, and it will remember what the rules are for which input parameters should it look for, what output parameters should it go for, and do its thing. Oh, and then I should mention that T-Rex clusters gets created as a parameter. What embed does not do, oops, not CDF, wanted a histogram. What it does not do is automatically gate the parameter. So I had to come in here and say right click, create gates on peaks. And then it gates these up so that I then have my T-Rex cluster populations that I can then look for frequency, whatever profile I want, apply MEM to it again, etc. So whatever you'd like to do at that point. Okay. With that, that is my high dimensional workflow of done, not discussed entirely, but Peacock run to clean up the data, followed by T-Rex to do dimensionality reduction and clustering, targeted toward the spots in the data that are different between some condition. Young and old was this example, could be any condition that you want to put in, annotated through a keyword. MEM then used to rename the clusters to something that means sense, that makes sense to me. That'll know what it is. It'll have a profile that anybody could talk about and say, well, it's high for that, low for that, compared to whatever my reference is. And then if we discover something of interest, we can use Embed to forward propagate it and make whatever discoveries we have actionable so that we can actually make this a foundational piece of some kind of, future, future workflow toward identifying specific subsets or kinds of differences in whatever your perturbation is. All right. I'm looking at the chat. I think we've hit the 2 questions that came up. Thank you, Stephanie. I appreciate some questions. Good interaction thus far. If you've got any other questions, feel free to type them in the chat. We're a minute past time at this point. So I will also just pop back up my initial slide that has my email address on it, john.flojo@bd.com. Feel free to write me in the future. And thank you for attending. You're welcome. Appreciate it, Claire. Trying it now. Even better, Oscar. All right. Have a great day.